Hello, welcome to our class today of STA 2306, which is real analysis real analysis for statistics. Now I'm expecting that this course will be taken by all the 5 groups from Stack. And my name is Mr. Siemo Michael. So the course outline for this course, before the course outline, the prerequisite you must have done the calculus 1, and also you must have done some algebra and some other basic mathematics units. So the course outline, we have the first topic to cover will be Fourier series. The second, in this Fourier series, we're also going to look at convergence theorem. We're also having application of Fourier series. It's nothing like Fourier's, so it is Fourier series. Also, we're going to have the sum of infinite series. Then the second, we're going to have calculus for several variables. Also, we're going to have continuity and differentiability. And differentiability. So going to have the first order partial derivative. First order higher and mixed. And mixed order partial derivative. Partial derivative. Also going to have the application of equations of tangent plane. Application of the application of tangent plane and unconstrained constrained optimization and constrained optimization. Also, there again, you're going to have infinite series. Under the infinite series, you're going to have the comparison. Number 3, have infinite series. Next series, look at the comparison. Comparison, ratio and integral test. And integral test of convergence. Convergence. Then number 4, do not have power series. Power series. Here we have the radius of convergence, radius of convergence. We also have absolute convergence, absolute convergence, absolute convergence. Then number 5, we have Cauchy principle of convergence. Cauchy principle of convergence. Convergence. Number 6, we're going to have stochastic and asymptotic convergence. Stochastic and asymptotic convergence. Convergence of probability distribution. Probability distributions. Probability distributions. Also, number 7, uniform convergence. Uniform convergence. We also have sequence of functions in series. Sequence of functions and series. The Weiss stress M test. Weiss stress. The Weiss stress M test. And the Cauchy principle of uniform convergence. And Cauchy principle of uniform convergence. Now, this is the causal trend of what we're going to cover. And some of the recommended books I'll share with you, class reps, and they're going to share with you. Some of them being like the real analysis by Emmanuel D, written in 2002. And also again, we have the introductory real analysis. You also have Guide to Analysis by Hart FM 2001. You also have another book on analysis by Kopp VE 1996. And finally, we have the fundamentals of real analysis by Foreign J in 1992. So that will be the course outline. And we're going to start by, first of all, reminding ourselves of what you need to understand before we start this course or this unit. And there we want to understand what do we mean by even function and odd functions. I hope that you did that in calculus. We already covered that in calculus, where you said that we have an even function, a function in which the f at negative x will be equal to the same as negative f of x. So let us start our class by, recalling the odd and even functions. So right here, even and odd functions. Now, what is an even function? So say that a function f of x is said to be an even function, said to be an even function if f at negative x is equals to f at x. Similarly, a function f of x is said to be an odd function if f at negative x, if f at negative x is equals to negative f of x. So you can look at what we mean by an odd function, this one here. The condition to be satisfied to be an even function is this one. And the condition to for a function to be satisfied as an odd function is this one. So these are things that I want us to recall because you have already covered them in various units. So it being an odd function and an even function. We can present this one, the two difference on a diagram. For instance, maybe you can have a sketch of a graph. So you can have a graph maybe for an even function, small sketch. So suppose maybe you have y is equal to a function of x. Then you can speak that an even function looks like that, maybe an example of the form like that. This one is even function. This is like, for example, maybe if you can have a quadratic equation, y is equals to maybe, for instance, maybe x squared. Then you'll find we have an even function. Y is equals to x squared, it's an even function. So this one here is y is equals to f of x. This is the kind of a graph that can resemble a function which is even. So this being the y-axis, and this one here being the x-axis. So if you can still do the same to an odd function, and then you see how does it resemble. So for the odd function, you can have a graph like that. And then now for this one here, I have maybe a function of the form. It almost resembles maybe a sine function. So this one here is an odd function graph. So this one is going to resemble the odd function graph. Still, this one is y is equals to f of x, and this one is y axis. This one is the x axis. So you can be able to see what we have, or maybe a sketch of an even function and odd function. If you check an even function, in this case here, it looks symmetrical, but it is not necessarily maybe it should be symmetrical. So let us look at some of the points maybe you need to rewrite when it comes to even function and odd function. So here we have some points to note, or NB. NB. Number one is that sum of odd powers of x are odd. So we say sums of odd powers, sum of odd powers of x are odd. Like for example, when you speak about odd powers of x. So remember we have even and odd. So odd powers we have, for example, maybe cubic, raised power 5, raised power 7, x raised power 9, like that. Those are odd powers, and therefore it will be odd. Then also number 2, but the second thing to note is that sum of even powers of x are even. Sum of even powers of x are even. For example, maybe x squared, x is power 4, x is power 6, x is power 8. So y is equals to x is power maybe 10. So it means that that function will be even function. Number 3, we also have sin x is odd. The function sin x is odd, and cos x is even. And maybe this one you have already proved, because you know that, for example, maybe f of x, if maybe can trace check whether it is true that sin x is odd. So if our f of x is equals to sin x, then for us to understand, or maybe for us to prove that a function is odd, they need to show that f at negative x is equals to negative f of x. Now, let us see. So in that case, you can say f at negative x is equals to what? Equals to sine negative x, like that. Now, if you check sine of 30, probability is 0.5. Now, sine negative 30 is equals to negative 0.5. So, if I can multiply the first one, the sine of 30, by negative, I can get the second one. If I can call this one the first one, and this one the second one, it means if I multiply the first one by negative, then I get the second one. So that implies that negative sine 30 is the same as what? Is equals to negative 0.5. So that one now indicates that f at negative x is equals to negative sin x, and sin x is our f of x. So we're going to have f at negative x is equals to negative the f of x. And now that one tells you that sine is an odd function. You do the same to cos, but now for the condition for even, we have said is that f of negative x is equals to f of x. So this one is the condition for even. Now, the next thing also to note is that the product of two odd functions, number 3, number 4, that is product of two odd functions is even. It's even. Like for example, maybe e.g. you can have an odd function. Y is equals to x is an odd function, and sin x is also an odd function. So if I have x sin x, automatically it becomes an even function. Then also you have number 5, product of two even functions is still even function. It's even. Listen to note. For example, maybe you can have two even function, like for example, x squared is an even function. We said from the second and the first condition, we say that if maybe the sum of even powers of x is also even. So x squared is even, and also cos x is even. So the product of these two, they still give us an even function. The other one to note, the product, number 6, product of an even function and odd function, product of an even function and odd function is an odd function. So for example, maybe we know that sin x is a, so e.g. sin x is an odd function and cos x is an even function. So if you can have sin x multiplied by cos x, this one here being even, being odd, this one cos x being even, it will result at odd function. So these are things that I want you to note before we proceed. Also, something else that you need to note. So we have also what we call the integrating of odd functions over symmetric domains. So we have integrating integrating odd functions, integrating odd functions over symmetric domain. Over symmetric domain. So in this, what do we say? We have, say, suppose you can let a positive integer p. So let a positive integer p be a fixed number. Positive integer p be a fixed number if f of x is an odd function. If f of x is an odd function, if f of x is an odd function, then the integral from negative p to p f of x will be equal to 0. Why I'm saying like it will be equal to 0? It's because it means now from negative p to 0, it is symmetrical, and therefore, so it's going to be like going to have from negative p to 0, f of x dx plus the integral from 0 to p f of x dx. The reason why, sorry, the reason why it will become equal to 0 is because it is symmetrical. So you'll find that this part, the answer will be positive. For instance, maybe you can say it is positive a. Then this part here will become negative a. So when we add the two of them, you'll end up getting a 0 because the domain is symmetrical. So what I can say about this, we can say this implies the area beneath the curve on closed interval from negative p to 0 is the same as the area under the curve in a closed domain that is on 0 to p, but opposite sign. And therefore, they cancel each other. They cancel each other. So you can see one will become positive, the other one negative, and therefore when you add the two of them, you get definitely a 0. Then also again we have integrating even functions over the same domain. So you can see when you're integrating an odd function over a symmetrical domain, then it will be equal to 0. Now, what happens if maybe the function is even? If the function is even, so let us have integrating even function, over symmetric domain, Now, in that, also say let P be a positive number, be a fixed number. If f of x is any given function, is any even function, is any even function, then the integral from negative p to p f of x will be equal to twice the integral from 0 to p f of x dx. Why is it so? Why is it so? We can say this implies the area beneath the closed interval beneath the curve over a closed interval, the curve on closed interval negative p to 0 is the same as the area under the curve, on the closed interval 0p, But now in this case, with the same sign, same sign. So you can find the area. So you can find the area on 0p and simply double and simply multiply by 2. That is, you double the area. Now, if you can do some little, we show graphically on what this entails is that for an even function, we have said you can have a graph of the form like this. So I want us to choose the two intervals. This one here it is negative p, here it is 0, and this one here it is p. Now, if we find the area under the curve, because remember integral is used to find the area under the curve. So meaning that if I integrate this function of this curve over the interval negative p to p, then I'll be finding the area of the red shaded region. And let us say that this one hits y equals to f of x, the function. This one hits the x-axis. This one hits the y-axis. So this means now this one here is an even function. This is for an even function. F of x is an even function. So if you can check this function of this curve, it is symmetrical about the y-axis. So this means that the area on the interval negative p to 0 will be the same as the area from 0 to p. And that's why you have said the integral from negative p to p f of x dx will be the same as 2 the integral from 0 to p f of x dx. That is what this diagram implies. Now, what happens when we go to an odd function? In the even function, you can see the area of this one here. If it will be positive, then also the other one is going to be positive. If the area of this one is going to be negative, then this other one also is going to be negative, right? Like it's the double. They are going to have the same sign. Remember, it is not necessarily maybe the function just to the graph to look up. It can also look down, and still it's an even function. Now, let us have an odd function graph. An odd function will look like this. We're going to have that, and then now this one is being our y-axis. This one is the x-axis. So we're going to have a graph of the form like that, so that if you can choose within a certain interval, we choose maybe from here, this one is our negative p, then this one here is p. So it is symmetrical about the y-axis. Again, this is the area that you can find if we integrate this function within the given interval. We're going to obtain the red shaded region. And if this area here will become positive, this one it is positive a, then this one it will be negative a. And if I add these two areas, they're going to cancel out. And that's why we have said if f of x is an odd function, then the integral from negative p to p f of x dx will be equal to the integral from negative p to 0 f of x dx plus the integral from 0 to p f of x dx. And so if this area here will be, it will be maybe, we talk of maybe positive, then plus. No, within that we have said it is negative. Then the area between in the interval 0p is an a. Then we're going to have what? 0. And that's why we have said this one here will be equal to 0. So these are things that you need to remember. So another thing we also need, we want to check, it is what we call a periodic function. What do we understand by a periodic function? What's a periodic function? So I can proceed and check a periodic function. Periodic function. Now, when you hear the term periodic, it brings the sense of repetition. After a while, it repeats itself. For example, maybe, before I write, if maybe I have sine 30, it will be the same as if I go a whole cycle, 360 degrees, so that now I'm going to have 360 plus 30, which is 390. They are going to have the same value. because it has now started to repeat itself after a whole cycle. So in that case, we can talk of sine being a periodic function. So we can also have cos the same way. So cos and sine, they are good examples of a periodic function. So we can define here a periodic function and say a periodic function, a function f of x is said to be periodic. A function f of x is said to be periodic if there exists a number t, that is a positive number t, such that f at x plus t is equals to f of x for every x. For every x. Full stop. So the smallest such number t, the smallest such number t is called the period. It's called the period of f of x. The period of f of x. So periodic functions have repetitive behavior. We have repetitive behavior. Full stop. A periodic function can be periodic function can be find a finite can be defined on a finite interval. Then copied, and pasted so it repeats. Maybe an example. We have said an example of a periodic function. We have sine x, okay, sine pi x and cos pi x are a periodic function. Or maybe they are periodic with period period 2. Now, this is because when we speak about, if you look at sine x, now sine x and cos x, they are periodic. They are periodic with period 2 pi. 2 pi is equivalent to 360 degrees. That means that sine x, it repeats itself after a whole cycle. After a whole cycle, you're going to have the same value. 2 pi are 360. Now, this one now tells us that in the first statement, this one, sine pi x, it is periodic with period of 2. The period of 2. So if you check, how did we get this period? 2. If you check the first statement and the second statement, in the second statement, it's like we have divided sine pi x by sine 2 pi x by 2 pi x by 2 pi. So you will realize that it is what we have in the denominator gives us the period. So it's going to repeat itself after 360 degrees. I've just given an example such we have said, if you look at sine 30 is equals to 0.5. So if you can go a whole cycle, we had 360. So we're going to have sine 390, which will still be equal to 0.5. So what you can do, maybe in the next class, we're going to start on Fourier series. Probably I'm going to send the next phase tomorrow. So this was the introduction for you to gain the understanding, or maybe also just to recap for you what you have already covered in the previous classes. What's an even function, an odd function, the integrals of even functions, the integrals of odd functions, the periodic functions. So remind yourself on more on that before we come and start. We continue the class on Fourier series. So when we meet next, you're going to start on Fourier series. We shall start on Fourier series. You can start here. Let me just put down the topic, Fourier series. We shall start on Fourier series. And we shall see interesting part of Fourier series. We're going to work with these periodic functions. So we're going to continue from the periodic functions to understand what a Fourier series is. So thank you very much. And let us meet in the next class.